I want to go a little bit into the details of finding PDFs for functions of random variables. So first, before we do this for jointly continuous random variables, so the multivariable case, I want to go back and talk about the single variable case first. And in particular, I want to just sort of give a little bit of a deeper sense for the details that we glossed over at the time. And so, if we have a continuous random variable x and y is some function of x, so we'll call it g of x. Well, we had this method for figuring out a PDF, a probability density function, for y. Right, so we found f sub y, right, the PDF for y, by first considering the CDF. So we considered the cumulative distribution function. All right, so let's just quickly run through how we did that. Right, we started off by considering the cumulative distribution function of y evaluated at some a. And the first thing to say is that, just by definition, this is the probability that y is less than or equal to a. Now use the fact that y is equal to g of x to say that this is the same as this probability. Right, and now we sort of glossed over what actually has to happen here, but generally speaking, what we did next was to either turn this into the probability that the random variable x was less than or equal to g inverse of a. Right, and the classic example that we used here was where the inequality was preserved was when g of x was something like e to the x, right? So the exponential function. And so its inverse preserves this inequality because it's an increasing function. Right, and we had another example that behaved a little bit differently. Right, so we also saw not where the inequality was preserved, but rather where it was flipped. All right, and the example here was when, the example we saw in class anyway, where this happened was when g of x was 1 over x. All right, so we've seen examples where both of these things can happen, where the inequality is preserved and where the inequality flips. But the thing that I really want to sort of harp on now that we haven't really talked about is the fact that right here, in saying either the blue statement or the yellow statement here, we need to know that g is invertible. Right? This was a rather big point that we didn't even mention when we were doing examples like this. So we need to know that g is invertible. And so I'm just going to sort of list some things that we need to know here. There are going to be two things that go into this list. The first thing we need is that g is invertible. And if you remember back from pre-calc or from Calc 1, effectively this just means that g has to pass the horizontal line test, right? If you look at a graph, y equals g of x. Or from calculus, it means that on its domain it has to be strictly increasing or strictly decreasing, right? Very much like the exponential function, strictly increasing, and 1 over x, at least for positive values of x, which was in the example we saw in class, the only place that we actually considered this, that is a strictly decreasing function. Right, so first thing, we need g to be invertible. Now, if that does happen, right? If G is invertible, then we can say this blue statement in the case where G is increasing, or we can say this yellow statement in the case where G is decreasing. Now we saw two slightly different flavors for what happens here, right? This blue statement is really a statement about the CDF of X, right? This is really the CDF of X evaluated at G inverse of A. And this yellow one, well, this is really a complementary kind of statement about the CDF, and so what we did there was turn it into 1 minus the cumulative distribution function of X evaluated at G inverse of A. All right, so a couple different ways that this calculation could go. Effectively turning this thing into a plus or minus situation, right, which we'll see in a second. All right, so when this happens, we get that F sub y, the CDF of y evaluated at A, is either equal to F x of G inverse of A, or 1 minus Fx of G inverse of A. All right, with the blue case corresponding to this option, and the yellow case corresponding to this option. All right, and the way we proceeded was to say that the derivative with respect to A of the CDF by the fundamental theorem of calculus will give us the PDF. Right, so taking the derivative here with respect to A will give us the PDF that we wanted. Right, this is what we were after to begin with. And now differentiating here inside the blue box by the chain rule, this will give us G inverse prime of A. And we need to multiply by the derivative of the CDF of X. And again, by the fundamental theorem of calculus, that's just going to turn into the PDF. And it's evaluated at the same place, G inverse of A. Right, so this is what happens in the blue box. And our second case is what happens in the yellow box. All right, so we're going to have or this happens, or the PDF for y, f sub y of A. This is going to be given by, now we're going to differentiate this expression here. The 1's going to vanish. We're going to get an extra minus sign. And then everything else looks the same. Oops, this should be G inverse prime of A, multiplied by the PDF for X, evaluated at the same place, G inverse of A. All right, so here, let me clean this up a little bit. Get this. All right, so we're just using the chain rule and the fundamental theorem of calculus in both cases. Now, the first thing that we need up here is that G is invertible. Implicitly here, these two, both the statements in these boxes really only work if G is not only invertible, but G inverse is also invertible. And if you remember back to Calc 1, when we learn about the implicit, the implicit function theorem, but really implicit differentiation is what we call it then. When we learn about implicit differentiation, one version that we learn is what happens when we differentiate inverses. Right, so long story short, what happens here is that we can calculate the derivative of the inverse just based on the derivative of the original function. So this is going to be 1 over G prime, so the original derivative, evaluated at G inverse of A. All right, so this is from Calc 1. And really this is just an application of implicit differentiation, which is really just the chain rule in disguise. So this is all just the chain rule, basically, on repeat. So not only do we need G inverse to exist to begin with, but we also need we need it to be differentiable, right? We need this derivative to exist. Otherwise, we can't really talk about this. And so the way that this is, right, what the statement, if you unpack it, is really saying is that G inverse is going to be differentiable when G prime of G inverse is not 0, right? When G prime exists, first of all, which all the examples we saw in class, it did exist everywhere, at least everywhere that the original function was defined. So that's usually less of a major point. And the really important thing here is that this denominator just can't be 0, right? That's really the most important part here. And so this leads us to a second point that we need up here. Right, the other thing that we need is that G inverse prime needs to be defined. And we can use this idea down here to sort of equivalently restate this as saying that G prime of G inverse should not be 0. All right, so assuming everything is nice and differentiable everywhere, or at least everywhere that we care about it, then this is saying enough. All right, so we somehow need these two things to be true in order to find a PDF, right? This is all in order to find the PDF f sub y, where the random variable y is some function g of the random variable x. All right, so what we're going to do next is figure out pretty much exactly how this actually tells us what we want to know, right? So before we do that, and when I say what we want to know, I mean now that we're in the context of multiple variables, right? We want to understand how this stuff works analogously when we have, you know, two random variables, x1 and x2, and we've rewritten two other random variables. Y1 is a function of both x1 and x2, and y2 is a function of both x1 and x2. All right, so basically just take everywhere you see a single variable and make it two variables. We want to understand what happens in that context. And before we do that, I just want to make one comment here, which is that we could rewrite, when 1 and 2 both happen, we can rewrite f sub y of a, right? This is really just plus or minus G inverse prime of a times the PDF for x evaluated at G inverse of a. All right, so I'm just incorporating this into one line here. It's plus or minus this, where it's not an arbitrary plus or minus. It's a very definite plus or minus, depending on whether or not G itself was increasing or decreasing, right? Think like e to the x versus 1 over x, right? Increasing versus decreasing. And using the inverse function theorem, right, this version of implicit differentiation that I just had on the board down here, this is the same thing as saying we're going to have, I'll just put the plus or minus in front here, plus or minus f sub x of G inverse of a. And now I'm just going to rewrite G inverse prime. This is G prime of G inverse of a. All right, and so what we're doing here is effectively just rewriting the right-hand side, rather than all being in terms of G inverse, like G inverse prime here, and G inverse on the insides. Well, what we've done here is just rewrite it in terms of the original derivative. And this is going to be much easier to generalize to the multivariable case for some reason, right? So we'll see why that happens in the next video.